Welcome to the Deep Dive, your shortcut to being genuinely well-informed. We dig into some really interesting source material and pull out the key nuggets for you.
Get you up to speed quickly.
Exactly. And today, we are taking a deep dive into Python programming. Now, you might hear programming and, maybe tune out thinking it's super technical. But really, understanding Python is kind of like understanding the language behind so much of our digital world. Think about the apps you use every day. A lot of them have Python involved somewhere.
It's pretty ubiquitous now.
It really is. So our mission today is to cut through the jargon, give you those aha moments, and hopefully leave you feeling pretty confident about what this really powerful tool is all about.
That's good.
Okay, let's unpack this. So to kick things off, the big question, what exactly is Python? We hear the name all the time, but at its core, what are we talking about?
Right. Well, basically, Python is what we call a high-level programming language.
High level. Okay, compared to what?
Good question. Compared to low-level languages where you're talking almost directly to the computer hardware, like really tiny steps. Think C++ or Java or PHP. Those are other high-level examples, too.
Oh, okay.
With Python, it's more like speaking to a really smart assistant. You give it broader commands, and it figures out the nitty-gritty machine instructions. This makes it way more human readable.
So easier for people to write and understand.
Exactly. And it's super versatile. I mean, you can use it for web development, building graphical interfaces for apps, automating tasks, all sorts of things. Plus, it's object-oriented.
Okay, object-oriented. What does that mean in simple terms?
It just means it bundles data and the functions that operate on that data together into these neat little packages, these objects. Think of them like building blocks.
Gotcha.
And here's something interesting. It's both strongly typed and dynamically typed.
Okay, strongly and dynamically typed. That sounds a bit contradictory.
Yeah.
It does, doesn't it? But strongly typed means it's strict about what kind of data you're working with, which helps prevent errors. Dynamically typed means you don't have to declare the type of a variable up front. Python figures it out on the fly.
Ah, I see. So it's flexible but also safe.
Exactly. It offers this great mix of flexibility, letting you code faster, but with safety rails. It really boils down to focusing on readability and productivity, which is great if you're learning or just want to get things done.
That focus on readability and being versatile sounds, incredibly appealing. And, the history of a language often tells you a lot about its sort of philosophy. So here's where it gets really interesting. Where did Python actually come from? What's the origin story?
Okay, so Python's story starts back in the late 80s, early 90s.
Wow.
Yeah, it was developed by Guido van Rossum. He was working at the National Research Institute for Mathematics and Computer Science in the Netherlands.
And what's cool is Python wasn't just invented out of thin air. Guido was inspired by a whole bunch of other languages that were around then.
Oh, like what?
Things like ABC, Module 3, C, C++, plus Go's, even Unix shell scripting and Smalltalk. So it's kind of a melting pot of good ideas.
So it borrowed the best bits from others.
You could say that, yeah. It's copyrighted, sure. But crucially, the source code is freely available under the GNU General Public License, the GPL.
And that openness is probably a big reason why it took off, right?
Oh, absolutely. Huge factor in its wide adoption.
And it obviously didn't just stop there. It's evolved quite a bit since the 90s.
Definitely. Python 1.0 came out in November 1994. That was the real start.
Yeah.
Then Python 2.0 landed in the year 2000.
Okay.
But the really, really big moment, kind of a turning point, was in 2008. That's when Python 3.0 was released.
Right. And Python 3 wasn't just a minor update, was it? I remember hearing it wasn't backward compatible with Python 2. That sounds like a massive, potentially risky decision for a popular language.
It was huge. Yeah, a very deliberate, significant break from the past. Not backward compatible at all.
So why do that? Why break compatibility?
Well, the core idea behind Python 3 was all about streamlining the language, making it cleaner, more consistent for the long haul. They wanted to get rid of some of the confusing bits and duplicate ways of doing things that had crept into Python 2.
Ah, okay. Tidying up.
Exactly. The guiding principle really became there should be one and preferably only one obvious way to do it.
One obvious way. I like that.
It's a core part of the Python philosophy, the Zen of Python. It forces clarity. For most common tasks, there's a single clear path, which really helps with reading code later, maintaining it, makes it easier to learn too.
That one obvious way idea makes total sense, especially if you're aiming for readability. So Okay, beyond that core design philosophy, if someone's just starting out, what are the killer features, the things that make Python stand out and give you those aha moments?
Right. For someone learning, Python's got some major advantages. First off, it genuinely is easy to learn, relatively speaking, of course.
Okay, why?
It just has fewer keywords to memorize compared to many languages. The structure is simple, the syntax is really clearly defined, you can pick up the basics pretty quickly.
Nice.
And that leads straight into the second point. It's easy to read, like Python code often looks almost like plain English or pseudocode. You spend less time figuring out weird symbols and more time understanding the actual logic.
Yeah, I've seen snippets that look quite intuitive.
Exactly. And practically speaking, that readability makes it much easier to maintain your code later on.
Okay.
As your programs get bigger, that becomes a massive advantage.
That makes sense.
Then,
And I've also heard people rave about its standard library. What does that actually mean for someone using Python day to day?
the standard library. Yeah, it's legendary for a reason. Basically, imagine you need to do something common, like connect to a database or work with web pages or process text files or handle dates and times.
Right, common tasks.
Instead of writing all the code for that from scratch, Python comes with this huge collection of pre-built modules like ready-made toolkits that handle tons of these common tasks right out of the box.
Batteries included, kind of.
Exactly. That's the phrase often used, batteries included. And these library modules are designed to be portable. They work across different operating systems, Windows, Mac, Linux.
Oh, wow. So if I write something on my Mac, my colleague on Windows can probably run it without issues.
Pretty much, yeah. For standard library stuff, it's designed to just work. It saves a massive amount of time and effort. And beyond the library, Python supports different ways of programming. You can write simple scripts or build large, complex applications using object-oriented principles. It even supports functional programming styles.
Flexible.
Very flexible. And it plays well with others. You can integrate Python code with code written in C or C++ig or Java if you need some heavy lifting done. Plus, it handles memory management automatically with garbage collection, which saves you a lot of headaches.
That automatic memory management sounds like a lifesaver. Okay, so this versatility, the library, the readability, it's a compelling package. Now, you mentioned Python is high level. How does a computer actually understand these high-level instructions? What's happening under the hood? You hear terms like interpreters, compilers.
Right, good question. So fundamentally, there are two main ways computers process these human-readable high-level languages. You've got interpreters and compilers.
Okay.
An interpreter basically reads your program line by line, or maybe a small chunk at a time, and executes it directly as it goes. Think of it like a simultaneous translator whispering the instructions to the computer.
Line by line. Got it.
A compiler, on the other hand, takes your entire program first. It reads the whole thing, analyzes it, and translates it all at once into a low-level language the computer understands directly, usually called machine code or object code. This creates a separate executable file.
Like translating a whole book before anyone reads it.
Exactly. You compile it once, then you can run that translated executable file many times without needing the compiler again.
So which one is Python? Interpreter or compiler?
Well, here's where Python is a little bit sneaky. It actually uses both processes.
Oh, how did that work?
When you run a Python program, it's first compiled down into an intermediate format called bytecode. It's not machine code, but it's a lower-level representation.
Okay, bytecode.
Then that bytecode is interpreted by something called the Python virtual machine, or PVM. So it's a compile step followed by an interpretation step.
Huh. So why do people usually call it an interpreted language then?
Mostly because that's how it feels to the programmer. You write your code, you run it, and you often get immediate feedback, especially in certain modes. You don't typically deal with a separate compilation step like you do with C++ or Java. That immediate interaction makes it feel interpreted.
Right, that makes sense. It's about the user experience.
Yeah.
And you mentioned different modes. How do people typically interact with this Python interpreter?
Yeah, there are two main ways. One is what we call shell mode or interactive mode. You basically type Python commands directly at a prompt. It usually looks like 3 greater than signs.
Okay.
And as soon as you hit enter, the interpreter executes your command and shows you the result. Like if you type print 1 + 1, it immediately prints 2 on the next line.
Instant feedback. Great for testing little things.
Exactly. Perfect for quick tests, calculations, exploring ideas, or debugging small snippets. The other main way is script mode.
Script mode.
That's where you write your Python code into a file, usually ending with .py, and then you tell the interpreter to run that entire file from start to finish.
So for actual programs.
Right, for anything more than a few lines. And nowadays, most people use an integrated development environment, an IDE like IDLE, which comes with Python, or others like VS Code or PyCharm. These usually give you both a place to write your .py scripts and an interactive shell.
Best of both worlds, then. Okay, so we write the code, Python interprets via bytecode, but let's be real. It doesn't always work perfectly first time, right?
Huh. Not usually, no. That's just part of programming.
Errors happen, and in programming we call them bugs, and finding them is debugging. What kind of hurdles, what kind of errors should someone expect when they're learning Python?
Yeah, errors are inevitable. Think of them as learning opportunities. Generally, they fall into three main categories.
Okay, 3 types.
First, you got syntax errors.
Huh?
These are like grammatical mistakes in English. Python has very strict rules about how code needs to be structured, where colons go, how things are indented, spelling keywords correctly.
Right.
If you break one of those rules, Python won't even try to run your code. It'll stop immediately and usually point you to the line where it got confused. These are super common for beginners because Python is pretty picky about syntax. One misplaced comma can stop everything.
I'm forgiving.
Very, but it forces you to be precise. Then the second type are runtime errors, often called exceptions.
Runtime errors.
Yeah.
So these happen while the program is running.
Exactly. The syntax is perfectly fine. Python understands the structure, but something impossible happens during the execution. Like maybe you try to divide a number by 0, or you try to access a file that doesn't exist, or use a variable that hasn't been given a value yet.
Okay. Things that only become problems when it actually tries to do them.
Precisely. The program starts running, then bam, it hits the problem, stops, and usually gives you what's called a traceback, an error message explaining what went wrong and where. It's telling you an exceptional and bad thing has happened.
Gotcha. So syntax errors, stop it before it runs. Runtime errors, stop it during the run. What's the third type?
The third type? These are the sneakiest ones. Semantic errors.
Semantic errors, meaning
errors in the logic of your program.
Yeah.
With semantic errors, your code is perfectly valid Python syntax. It runs completely fine, no error messages, no crashes.
Okay. So what's the problem then?
The problem is it doesn't do what you wanted it to do. It does exactly what you told it to do, but what you told it to do wasn't actually the right logic to solve your problem.
Ooh, that sounds tricky. Like the computer is following instructions perfectly, but the instructions themselves are flawed.
Precisely. It's like giving someone perfectly clear directions to the wrong address. They'll follow them perfectly, but they won't end up where you intended. Finding these often requires careful testing and working backward from the wrong output to figure out where your logic went off the rails. These can be the most frustrating to debug.
I can imagine. That distinction is really helpful, especially the semantic error, doing what you told it, not what you wanted. So, okay, stepping back a bit, what does all this mean in the bigger picture? How do programming languages like Python fit into, the whole world of communication, thinking about formal versus natural languages?
That's a really interesting comparison, actually. We live our lives swimming in natural languages, English, Spanish, Japanese, whatever.
Right, the ones we speak.
Yeah. And they're messy. They evolved organically over centuries. They're full of ambiguity. One word can mean multiple things. They have redundancy, idioms, metaphors. It's raining cats and dogs. Doesn't mean animals are falling from the sky, right?
Yeah.
Right? We rely heavily on context.
Definitely.
Formal languages, on the other hand, are different. They are designed by people for specific purposes. Think about mathematical notation or chemical formulas.
Okay, very precise.
Exactly. They're designed to be nearly or completely unambiguous. A statement has one specific meaning regardless of context. They're concise, literal. There's no room for poetic license or suggestion. And programming languages, like Python, are definitely formal languages. They were specifically designed to express computations, to give instructions to a machine.
So they share some features with natural language, like words, tokens, and grammar, syntax.
They do. Both have tokens, structure, syntax, semantics, meaning. But the nature of those things is profoundly different. In a formal language, the meaning is tied directly and unambiguously to the tokens and structure.
Right. I read somewhere it's like the difference between poetry and prose, but even more extreme for programs. Poetry is evocative, ambiguous. Prose is clearer. Programs are utterly literal.
That's a great analogy. Yeah. A program's meaning can be understood entirely by analysis of the tokens and structure. There's no hidden meaning, no cultural context needed beyond the rules of the language itself.
And that's probably why learning to program can feel weird at first, right? We're so used to the fuzziness of natural language.
Absolutely. People constantly use context and make assumptions when they communicate naturally. Formal languages demand absolute precision. That adjustment, thinking in such a literal, unambiguous way, can be a real hurdle when you're starting out. It's a different mindset.
That makes total sense.
Yeah.
A mental shift is required. Okay, so let's make another shift now, back to the practical side. If we want to actually build things in Python, what are the fundamental ingredients? The nuts and bolts.
Okay, the building blocks. Well, at the most basic level, you have values and types.
Values and types.
A value is just one of the fundamental things a program works with, like the number 2 or the text hello world.
Simple enough.
And these values have different types. 2 is an integer. Hello world is a string. You can usually spot strings because they're wrapped in quotation marks. Python has other types too, like floating point numbers, numbers with decimals, and booleans, true or false.
Got it. So values are the data itself. What about variables?
Right. Variables are basically just names that you use to refer to values. Think of it like putting a label on a box. The box contains the value, the label is the variable name.
So you can refer to the data easily.
Exactly. You create them with an assignment statement, like age 30 or name Alice. Now, age refers to the value 30, and name refers to Alice.
And are there rules for naming them?
Yep. Good practice is to choose meaningful names, obviously. Technically, they have to start with a letter or an underscore, can contain letters, numbers, and underscores. Importantly, case matters. Age is different from age.
Okay, case sensitive.
And you can't use Python's special keywords as variable names. Keywords are reserved words like if, for, class. Python has about 31 of them, I think.
Gotcha. So values are data, variables are names for data. How do we do things with the data?
That's where operators and operands come in. Operators are special symbols that perform computations. You know, like plus for addition, for subtraction, for multiplication, for division.
Standard math symbols.
Mostly, yeah. And the values that the operators work on are called operands. So in the expression 5 plus 2 plus is the operator, and 5 and 2 are the operands.
Okay. And combining these gives you an expression.
Exactly. An expression is a combination of values, variables, and operators that the Python interpreter can evaluate to produce a single result, a single value. 5 plus 2 evaluates to 7. Age 2 would evaluate to 60 if age is 30.
Makes sense. Now, you mentioned different data types. What about ways to organize collections of data? I hear about lists and dictionaries and brackets and braces.
Right. Organizing data is crucial. Python gives you some great built-in structures for this. The main ones you'll encounter early on are lists and dictionaries. And yes, they use different kinds of brackets.
Okay, so lists first. Square brackets.
Yep, square brackets are for lists. A list is basically an ordered sequence of items. You can put anything in a list, numbers, strings, even other lists. The key thing is that the items have a specific order, and you access them using an index number, which starts from 0.
The zero-based indexing, right?
Yeah.
So the first item is index 0, second is 1.
Exactly. So if you have my list equals 10, 20, 30, then my list 0 gives you 10, my list 1 gives you 20.
Okay, ordered sequence, accessed by number.
Yeah.
What about dictionaries then? Curly braces.
Right. Curly braces are for dictionaries. Dictionaries are a bit different. They store collections of key value pairs. Instead of accessing items by a numerical index, you access them using a unique key that you define.
Key value pairs.
Yeah.
Like a real dictionary, word and definition.
Exactly like that. The key is like the word, the value is like the definition. So you could have something like student name, Alice, age, 21, major, physics.
Ah.
Now, instead of using an index like 0 or 1, you use the key. Student name would give you Alice. Student age would give you 21.
That seems much more intuitive for certain kinds of data. Instead of remembering index 1 is age, you just ask for age.
Precisely. It's super convenient for representing records or mapping meaningful labels to values. One little thing to note is that traditionally, dictionaries didn't guarantee keeping items in the same order you added them, though in recent Python versions they do. But the main access method is always the key.
Okay, that's a clear difference. Lists for ordered sequences by index, dictionaries for unordered key value lookups.
Got it.
Now, back to those expressions with operators. If you have something complex, like 2 plus 3, 4, how does Python know what to do first? Addition or multiplication?
Good question. It follows the standard mathematical order of operations, often remembered by the acronym PEMDAS or sometimes BODMS.
PEMDAS. parentheses, exponents.
Exactly. Parentheses first, anything inside gets evaluated first. They have the highest priority, and you can use them to force a specific order or just make things clearer.
Okay.
Next is exponentiation, like raising to the power of, usually in Python. Then comes multiplication and division. They have the same level of precedence, and if you have both, they're evaluated from left to right.
Left to right, okay.
And finally, addition and subtraction plus bulk. They also have the same lower precedence and are also evaluated left to right.
So in 2 plus 3, 4, multiplication comes before addition.
Yep. 3, 4 is 12, then 2 plus 12 is 14. If you wanted the addition first, you'd use parentheses 2 plus 3, 4, which would be 5, 4, so 20.
Got it. And the advice is probably...
When in doubt, use parentheses. Seriously. Even if you know the rules, adding parentheses often makes your code much easier for humans to read and understand instantly. It removes any ambiguity.
Solid advice. Okay, so we have the building blocks, the operators, the order. How do we make programs do more interesting things, like make decisions based on data or repeat steps? That sounds like control flow conditionals and loops.
Absolutely. That's where programming logic really comes alive. We need ways to control the flow of execution. Conditional statements are how programs make decisions.
Like IF statements.
Exactly. The basic IF statement checks a condition, a logical expression that evaluates to either true or false. If the condition is true, then a block of code right underneath it gets executed.
And that block is defined by?
Crucially, in Python, it's defined by uniform indentation. After the if statement line, which ends in a colon, the code that belongs to that if must be indented, usually by 4 spaces.
Indentation is actually part of the syntax, not just for looks.
It is the syntax for blocks. It's fundamental. If the IF condition is false, that indented block is simply skipped.
Okay. What if you want something to happen when it's false?
Then you use an LSE statement. So you have IF condition, then the indented block for true, then ELSC, on the same indentation level as the IF, followed by its indented block for when the condition is false.
If this, do that, otherwise do something else. Makes sense.
And you can chain them with elif, elsif for multiple conditions, or even nest them, put an IF inside another IF or ELSC block. But again, keeping track of that indentation is key. Proper indentation is everything.
Got it. Indentation, indentation, indentation. Now, what about repeating things, loops?
Right. Loops are for repetition. Python has 2 main types, the for loop and the while loop.
Okay, for loop first.
The for loop is great when you want to iterate over a sequence. That means step through each item in something like a list or each character in a string. We often call this traversal.
So it goes through each item one by one.
Yep. You'd say something like 4 item in my list. In each pass through the loop, the variable item takes on the value of the next thing in my list. The indented block after the colon runs once for each item. You could use it to, say, add up all the numbers in a list.
Handy. And the while loop.
The while loop is different. It keeps repeating a block of code as long as a certain test condition remains true.
As long as it's true. So you might not know how many times it'll run beforehand.
Exactly. That's often when you use while. The condition is checked before each potential iteration. If it's true, the indented block runs. Then the condition is checked again. As soon as the condition becomes false, the loop stops, and the program continues after the loop's block.
Okay, like waiting for user input until they type quit.
Perfect example. You'd have a while loop that continues as long as the input isn't quit. And like if statements, loops can also be nested a loop inside another loop, which is useful for working with grids or tables of data.
Okay, for iterating over sequences, while for repeating as long as a condition holds. Now, sometimes within a loop, maybe you need even finer control. Like, what if you need to stop the whole loop early, or maybe just skip the rest of the current iteration and go to the next one?
Good point. Yes, Python gives you tools for that too. The break and continue statements.
Break and continue. Okay, what does break do?
The break statement immediately terminates the loop it's inside. As soon as Python hits a break, it just stops executing the loop entirely and jumps to the very next statement after the loop's code block.
Stops it dead. Even if the for sequence isn't finished or the while condition is still true?
Yep. Instant stop. If you have nested loops, break only stops the innermost loop that it's directly inside.
Got it. Innermost loop only. So what about continue?
Continue is different. It doesn't stop the whole loop. Instead, it skips the rest of the code inside the loop for the current iteration only.
Skips the rest of the current pass.
Right. So when Python hits continue, it immediately jumps back to the top of the loop to start the next iteration, if there is one. It doesn't execute any of the lines below the continue statement in that particular pass.
Can you give an example?
Sure. Imagine you're looping through a string of characters, printing each one. but maybe you want to skip printing the letter I. Inside your loop, you could have an if statement. If character, I, continue. When it hits an I, the continue would make it skip the print statement for that I and go straight to processing the next character.
Ah, okay. So break exits the loop completely. Continue just skips to the next iteration.
Yeah.
Very useful controls.
They are. And just one last time, because it's so important in Python, all these structures, if, else, elif for while, and the blocks they control rely absolutely on proper indentation to define their scope. Get the indentation wrong and your logic falls apart.
Understood. Indentation is king in Python. Wow. Okay, that was quite the journey through Python's core ideas.
We covered a lot of ground.
We really did. So just to recap for everyone listening, you now have a much clearer picture of what Python is, this high-level, readable, versatile language. We touched on its history, that interesting evolution from Python 2 to 3 with the one obvious way philosophy.
Right. Mm-hmm.
You've heard about the key features that make it great for learners, easy to learn, read, maintain, that amazing standard library, how it handles different programming styles.
Mm-hmm.
We even peeked under the hood at interpreters, compilers, and Python's hybrid approach.
And the inevitable bugs.
Yes. Syntax, runtime, and those tricky semantic errors. Plus, the whole idea of formal versus natural languages, which really frames how you need to think when programming.
Right, that precision.
And then we dug into the real building blocks. Values, types, variables, operators, PIM-to-days for order, and the crucial difference between lists with and dictionaries with.
Essential stuff.
Absolutely. And finally, controlling the flow with if-else for a while and fine-tuning with break and continue, all held together by
Indentation.
indentation. So hopefully you feel much better equipped now, not just to understand Python discussions, but maybe even to start exploring it yourself. It really does open up a lot of possibilities.
It really does. And maybe a final thought to leave you with, circling back to that idea of the semantic error. The program doing exactly what you told it, not what you wanted. Just think about how often that might happen outside of programming, and how we give instructions or set goals or communicate complex ideas in everyday life. Are we being precise enough? Are we conveying what we actually intend?
That's a really interesting parallel. Making sure your code for life matches your intention. Something to definitely ponder.
Worth thinking about.
Thank you so much for joining us on this deep dive. It's been incredibly insightful.
My pleasure.